All right, so up until now, we're going to start a chapter, but up to now we've been doing sample proportions and using those proportions to draw inferences about a population. So now in 23, we're going to make a transition. We're transitioning away from using just proportions to using actual sample means. So what we're saying is that if I take an average value of some population, of some characteristic about the population I care about, we're going to use a sample to try and make some type of estimation about the population itself. Okay. Now, in previous chapters, we've been giving the standard deviation of the population. Reality, we rarely actually know the standard deviation of the population. In other words, what we normally do is we use it from our random sample. Now, the problem with this is, in random samples, we're dealing with small samples. We don't usually have all of that about everyone. Instead, what we have to do is we have to make certain inferences based on that. And previously, this was a very big problem because we had the normal distribution. Normal distribution is very powerful, provided we have enough information. So one of the things that we've had to do is we had to come up with other types of distributions for when we dealt with smaller sample sizes, when we didn't know the standard deviation. Well, that's when we use a thing called the t-distribution. And that's a group of distributions that look a little like the normal distribution, except their peaks are a little lower. Their tails are a little fatter. And what that does is it gives us more opportunity to vary away from the mean. And these turn out to be much more accurate when dealing with small samples. So these t-distributions get their name from someone in history who, I don't think I'm going to go to it right now, but the main thing to remember is as our sample sizes get larger, they actually become more like the normal distribution. In fact, technically, once you have an infinite number of what's called degrees of freedom, and we're going to go into what those are, then you have the normal distribution. So in order to do this, like I said, for one sample test, what we have is called the degrees of freedom. These you need to know degrees of freedom to use the table. It is one less than the sample size, and that's what determines which of these tables we're going to use, which of these values we'll end up using. But a few things you have to note about t-tables in our situation here. First, when the standard deviation parameter is estimated from a sample, we call that statistic the standard error. We're not going to call it the standard deviation. We're using a sample to get it. It's the standard error, just like our samples have errors. Second, the standard error of the sampling mean is given by the function standard error of the mean, and it's equal to the sample's standard deviation. And since I keep saying all these symbols, let's mark some of them as we go. Right? So the standard error of the mean is equal to the sample's standard deviation divided by the square root of the sample size. Now, if a sample mean x bar, the sample t statistic, we don't have a normal distribution, so we don't have a z-score anymore. Instead, we're going to have what's called the t statistic. It looks a lot like the z-score, though, in that it's given by the t statistic is the sample mean we're investigating minus our null mean, what we think we're doing testing here, what we think the mean should be, divided by the standard error of the mean, or the sample standard deviation divided by the square root of the sample size. And of course, we have to remember it comes with n-1 degrees of freedom. Now, briefly, just because it's a fairly common question, what is a degree of freedom? Well, let's say I had 4 numbers, and there were the numbers 1, 2, 3, and I don't know what the next one is. And we had to say, well, they're average, though, so if we divided all of them by 4, and we knew the average was going to be 2.5. Well, at this point, I can figure out what that last number is. I have freedom in the first 3 numbers. They're my degrees of freedom. But once those 3 numbers are locked in, my 4th number, my last number, is automatically locked in. In fact, in this case, x has to be 4. Otherwise, I'd have 1 plus 2 plus 3. Well, that gives me 6. Well, I know 4 times 2.5, that's 10. X must be 4. So what I could say is I have these 4 numbers, and I add them up and divide by 4. and I get 2.5. Well, I can change A, B, and C as much as I want. I'm free to make them whatever I want them to be. However, when I have finished changing A, B, and C, I have no freedom with D. D has taken on a fixed value at that point in order for my mean to still be 2.5. So degree of freedom is just talking about how many of these could I change? Well, I have 4. I could change 3 of them, but the 4th one at that point is going to be locked in. That's where a degree of freedom is kind of talking about, so you can think about it that way. But we want to use that T statistic we came up with, and like I said, degrees of freedom, a lot of people get asking about it, so I decided to cover it very briefly what it is. But we're going to figure out our confidence interval from a T statistic. Well, it has this form. Our X bar, let's go back to our highlighter again. Okay. X bar, our sample mean that we found, plus or minus our critical value of T, and we're going to cover where that one comes from, times our standard error that we've been talking about now, our standard error of the means. Now, in order to do this, we're going to use certain tables from the book. We have to look up the correct degrees of freedom, and then we say, well, how confident do we want to be? And let's say I want to be 90% confident. Well, that means I'm working with that 2 tails area. That's my middle area. Let's change our color. My middle area is the 90%. And the way I'd use my book would I'd have 90%. 1 minus that, well, that leaves 10% left over. So my proportion 2 tails combined is my 10%. Oh, didn't quite mean to do that. Let's clear that out so we can see that a bit more. That's a bit too much. Okay. So I know I'm in this column. So if I go in this column and come all the way down, this is a column I'm going to be dealing with. Let's just say I had 9 degrees of freedom. And it might be a little hard to see here, but that'll be this row. So if I follow this row, that's the row I'm looking at. Now the intersection of those, now I find 1.833. That would be my critical value for T, 1.833. Now the other way we can do this is the way we've been doing a lot of this so far, which is using the calculator. But now instead of using inverse norm, we're going to use inverse T because we're done with T tables. That function in the calculator looks a lot like normal, and I have a separate video I've put together that shows how to do this in the calculator that you can watch to see that. Now, just like before, we're still going to have some conditions that we have to check. Now, our first one, of course, is our independence assumption. In order to prove our independence assumption, or in order to justify that assumption, first thing is it reasonable that this is going to have independence in it? We have to look at the sample and say, is it reasonable that this sample is independent? Part of that is, was it a random sample? That's going to help justify our independence assumption. But secondly, did we make sure we sampled less than 10% of the population? So another very important thing we have to do. Now, going along with all of this, we have another assumption that we're going to deal with. And it's called the normal population assumption. And what we're doing is, our data is coming from a population that follows a normal model. Now, this is an assumption because, as we said, we don't know that our population follows a normal model. Now, there are some times where you're going to be doing something where you kind of know the population is normal about that. But what we do is we use a nearly normal condition. If our data comes from a distribution that's unimodal and symmetric by making a histogram, or we can do the normal probability plot. We're going to go into how to do both of those. But a unimodal symmetrical distribution of a histogram, or as we said, the normal probability plot, which is one I personally prefer a lot of times, which simply looks like this. It's a nice linear collection of our data. And we'll go into how to make all these. A little coffee time. So let's say I've got a coffee machine. It dispenses coffee into paper cups. Now you're supposed to get 10 ounces of coffee, but the amount's a little different from cup to cup. So here are the amounts measured in a random sample of 20 cups. We want to know, is there evidence the machine is shortchanging customers? So in order to do this, we're going to have to use this sample. So we've gone out, we've taken a sample, and first thing I have here on the screen is it says fill it up, L1. So we want to put our sample inside of L1. We know we're going to have to deal with this data in a little bit. So let's go ahead and store that in L1 now. So pause video while you get this loaded in your calculator. Okay, so should be back, should be already recorded in the calculator. So first we have to deal with is a simple question of, well, what is our parameter? What are we investigating? Well, to be very straightforward about it, we need to define that parameter. Okay, all of this should be inside the notes that you could have printed out already. First one is the true average amount of coffee dispensed in a cup. Here, we're talking about how many ounces of coffee show up inside the cup. So our hypothesis, remember the question is, are we being shortchanged by the machine? The null hypothesis is that nothing is happening, which would mean that our null hypothesis is that the mean number of ounces of coffee made a cup is equal to 10. And the machine is dispensing an average of 10 ounces of coffee per cup. Our alternative hypothesis, that's what we're trying to find evidence for, are customers being shortchanged? Or are they getting less than 10 ounces per cup? Is the machine dispensing less than 10 ounces of coffee per cup? In order to do this, we're going to have to pick a model. Now, our model is going to be at this point a one mean t-test. Because we only have a sample of 20. We don't have hundreds and hundreds and hundreds. We don't know if it's normally distributed. We know we're going to be doing a t-test. So our models, first of all, do we have a random sample? And yes, we did. We had 20 cups of coffee. That's less than 10% of all the cups of coffee out there. We have no reason to doubt the independence. Okay. So we have to look into our histogram. Now our histogram from this, it looks like what we had on the rough. It's on the right here. It's roughly unimodal, roughly symmetrical. It's reasonable to think the amount of coffee in all possible cups could be described by a normal model. Now doing this to a calculator, we'd have had to load in all our data, and then we'd go into our second y equals. We have to make sure we had a histogram, and then we'd have plotted it, and we saw it, it wouldn't have looked anything like that. So we'd have had to hit window. And in window, we'd have changed some values around and changed an x scale to 0.1, and eventually we'd have gotten this. But we have to play around with it a bit to find that value. The other way we can do it is by using the normal probability plot. Okay. Personally, it's one I like. This is one where once we see we have a linear plot, well, it's done. And we can do it just like before. We do second y equal to get there. We choose our very last option for the type and tell it our data is in L1 and we're going to put on the x-axis. And this is what our calculator outputs. This is a nice, pretty linear looking plot, follows a straight line. So we'd say, yes, we match a normal probability plot. That justifies my saying the distribution appears to be nearly normal. Well, with this in hand, we've now met our assumption and conditions. We can go ahead and move forward with our test. So we can do the t-test for 19 degrees of freedom. We had a sample size of 20, so we have 19 degrees of freedom. We follow our mean. So our mechanics, well, we had 20. Our degrees of freedom, we had 19. The mean of those 19 samples, well, that's going to be 9.845. So let's go ahead and show that real quick. I've already taken the moment, loaded it in here. So I would hit stat, calc, one variable. It's set for L1. And I find my mean to be 9.845. My standard deviation, we can see right here, is 1.99 because it's a sample. So it's only 1.99. I'll pull back up our slides again now. Okay. So 1.99 for our sample standard deviation. And we know we're looking for this portion. Now, we're not sure where these values are yet, so let's find those. In order, we have to find our t-statistic, which is 9.845 minus our null hypothesis value of 10 divided by our standard error of the mean. So we get a t-statistic that we're looking for of negative 3.49. So we're down here. That's what we're looking for. Looking for that area of the graph or less. We find that. That's our p-value. That area is going to be our probability of this result occurring just by chance on a t-table with 19 degrees of freedom. We're looking for the probability of a t-value for 19 degrees of freedom of less a t-statistic. Let me re-say that. Our p-value is the probability that on a t-table of 19 degrees of freedom, we'd have less than negative 3.49 for a t-statistic. Which using that as tcdf is our command and calculator, our second vars, negative 99 all the way up to negative 3.49. with 19 degrees of freedom. It's not going to let you put in different means or anything. You have to convert to a t-statistic to use the t-CDF. We do that, we find the probability is 0.0012. That's our p-value. At this point, you should be saying, wait, I have a p-value, I can make a conclusion. And yes, you can. Specifically, it looks like from such a small p-value, it's unlikely that this low sample mean resulted just from sampling error. So we reject the null hypothesis. The null hypothesis was that there's nothing odd going on. Instead, there is strong evidence that the mean amount of coffee being dispensed by this machine is less than the amount of coffee they said we were getting. That's not right. People don't like you messing with their coffee. So that was our first example question. We're going to continue off another example question in class. So make sure you bring, our confidence interval. I'm sorry, last thing we should cover first. So confidence intervals, once we reject the null, we should be going to a confidence interval. This is what we're going to pick up on in class, is calculating our confidence interval. We'll create a 95% one sample t interval. So I look forward to seeing everyone in class soon. I hope you had a great weekend, and I'll talk to you later.